For question 11, we have a rectifying circuit, so it's a half-wave rectifier, right? So we have on the primary 120 volts RMS and then 60 hertz as the frequency. And we know that at the secondary Vs, so the input voltage for the rectifying circuit is 10 sine of omega t. So we need to sketch both input and output waveforms on the same graph if the diode is ideal, right? And also in this case, what would be the average DC content in the output, and what would be the required peak inverse voltage rating to the diode so it works properly in this particular circuit. Okay, so if you look at this circuit here, basically what happens is that at the input you would have a sinusoid. Okay, so I will represent this sinusoid like just a single period. So one period here it's 1 over 60, right? And half the period here it's 1 over 120. Okay, so the input voltage would be something like a sinusoid. So it's right here, goes down here, up there. So that's our sinusoid, and this would be 10 volts. So this is voltage, this is time, and this would be minus 10 volts. Okay, so this is the input. So let me draw it here. This is the input voltage. Now, if you look at this circuit here for the half-wave rectifier, it basically corresponds to a circuit that it's just a voltage source, or like, let me draw it like a sinusoid. Then we have the diode here, and then we have our load here, and then we are measuring this voltage here across the load, right? So we know that for an ideal diode, it just conducts current, or it allows current to flow only on a single direction like this, right? So if the potential here is positive, because we know that once it's open, this is 0, so this is, we suppose we have the ground here, right? So for a positive value of voltage, this diode is a short circuit. And then the value of the voltage that we measure at the output is just Vs. So if we look at the entire period here for the input voltage, the only region where Vs is positive is on the first half cycle. So this would be exactly the output voltage, okay, for this half cycle. Now on the second half cycle, what happens is that Vs is always negative. So the diode, in this case, the ideal diode, would be reverse biased. And if it's reverse biased, it becomes an open circuit and no current will flow. So the overall voltage measured at the out here would be 0. So from 1 over 120 would be up to 1 over 60, that would be 0. So this is the graph. Okay, so we have the input and the output. Okay, now how do we calculate the average? So the average is just the integral 1 over the period times the integral from the entire period. Okay, so that's the average. It's like the area divided by the time. Okay, or the entire period. So the V average, let me write it down, it's 1 over the period integral from 0 to the period of our output t dt. So what we have here in this waveform, right? So we have that the average is going to be 1 over the period. The period is 1 over the frequency. So 1 over 60, it just becomes 60, right? Now our V out of t, we can like split into two regions. Okay, so the first region is this region here from 0 up to 120, where the V out is equals to the input. So it's 10 times sine of omega t. Omega, you know that it's 2 pi f, so it's 2 pi 60 times t, times t dt, and plus 60 times from 1 to 160, 1 over 60. But now in this region, the integral is 0 dt. So we can just remove this part here because the integral of 0 is going to be 0. So I'm just ignoring this second part, right? So let's just ignore it. And the average voltage would be calculated at this value here. So the average is going to be 60 times 10. Now, the integral of sine is minus cosine. It's integral of sine of at, so it's 1 over a. So we divide this by 2 pi times 60 times cosine, so it's negative here, cosine of 2 pi 60 t, okay, from 0 up to 1 over 120. Okay, so if we evaluate this integral here, the average is going to be equals to 3.18 volts. So that's the average. Now, what about the peak inverse voltage? So if you look at the circuit here, during the second half cycle, the diode becomes an open circuit, right? So it becomes a circuit like this. Here, have our load, right? And this is the voltage that's been across the diode, right? So it has to support this voltage. It can't like blow up, or like if the voltage VD reaches some specific point. And in this case, when it is an open circuit during this period of time here. Now if you look at the maximum voltage that this VD, because in this case VD would be equals to Vs. So the minimum, or like the peak inverse voltage, would occur exactly at this point here, which is minus 10. So we say that the peak inverse voltage in this case is 10 volts. That's the maximum peak inverse voltage, or like it is the peak inverse voltage that the diode is required to support in this particular circuit. Okay, so that's it.